So we got I, double I, triple I, and IV. Read those four situations. And then we have four graphs on the right that relate to these situations. So what we're looking at, we've got to focus on the rate of change or the slope. Okay, they're the same thing. So is the slope increasing, decreasing, constant? Does it go up and down? What about the temperature of a hot tea over time? So first of all, where's it going to start? The temperature of hot tea, Harry? Yeah, it's going to start up top. So already you can kind of eliminate A and C, right? Because those ones start low. The temperature just doesn't magically increase. It's already hot, hence hot. So it's either B or D. So let's see. Does the temperature decrease or does it go down and then up? Yeah, it's got to be B. Okay, it's got to be B. So this would be the temperature, capital T for temperature, and time would be your independent variable and be the little t. Please mark that on there, Jiwa. Big T, little t. Did you mark this on the graph, or are you too busy talking? You sure? Okay, didn't look to me like you touched the paper. Sorry about that. Good. What about the speed of bike as it goes up a hill and then down? I don't know. What do you think? As you go up, as you're going towards the hill, what are you going to try and do?
You're going to try and go up a hill, which is going to slow you down.
When you go up it, your speed goes down.
And when
Exactly.
you go down,
so you're going up the hill, your speed's decreasing, you get to the top, and then your speed increases. So this is definitely D. And so we're going to be graphing speed, which is the letter S, versus time. Okay. Next one, a car accelerating at a constant speed, underlying constant. So what we're going to see there is this a steady increase. That's got to be A. Okay, so it's a steady increase. So this would be distance over time, and you're going to be going the same, just increasing at the same speed, constant. Height of a football, when you kick it, well, that's got to be C, right? You give that football a boot, it goes up in the air and comes back down. And so this would be your height versus time. So you got to come up with that. Given a scenario, you have to come up with what would that graph look like. What about Ferris wheel?
wouldn't the, couldn't you also put, instead of T on graph C, couldn't you also put D? Wait, no, then distance never goes down.
Okay, yeah. So it says here, label the independent and dependent variables on the graph. So here is your independent variables, and over here will be your dependent variables. So we've already listed them: distance and time, temperature and time, height and time, speed and time. Where do we usually find time? Yeah, it's the independent variable, which is the x. So this would be your x values, independent, and your dependence would be your y values. Okay. So time is 90%, 99.999 independent. Okay. Good. Summary. When comparing two quantities, straight lines are used to indicate constant rate of change. Okay. The steepness of the line indicates the rate at which one quantity is changing. Okay, so steepness or the slope is indicating the rate. Curves are used when the rate of change is not constant. So if your speed's increasing or decreasing, you would see a curve. Okay, here your speed is decreasing, here your speed is increasing. Sorry, got that wrong. Your speed is increasing. There you go. Okay. Don't worry about it. You don't need to know it. Okay. Horizontal means no rate of change. Okay, so no rate of change for horizontal. That's important. Okay. All right. have a look at the graph. Please read the part B and those 3 questions. Go. A. Tia. How long was it in the air? It left the ground here, landed here. How long was that? You got it. 15 minutes. Okay. So it's the entire time. B, what was the plane's maximum height? Well, it goes up to a maximum of right here, and that would be 6. Okay. Is that 6? Oh. How did I know it was 15 minutes? How did I know it was minutes? Yeah, because of the units and brackets. But how do I know that it's 6? Is this 6 kilometers? What would be for the height? Meters. So this person graphed wrong. 6 meters. M. So please put the M in brackets. That's really important that you put your units in brackets. Okay. And so this should be 6 meters. What was the total vertical distance? Now be careful because the answer is not 6. Remember, you got to go up and down. So here you go up 6. Here from C to D you go down what? Then from D to E you go up what? And then you go down. So altogether, what was the change? 6 plus 2? Plus 2? Plus 6? Right? So I add them all together. Okay, I'm not looking for the displacement or the net. I'm looking for the distance traveled up and down. So even though you go down 2 meters, you still travel 2 meters. Okay, so you're looking kind of like the absolute value of it. Good. So what they'd like to do then is have you describe that in words, because the words are going to help us make meaning of it. So we're going to look at each segment individually. At AB, what happened there? Yeah, plane took off. So it left the ground. And what did it do? Good. So it rose 6 meters in how many minutes? 3 minutes. So I'm describing the section. How did it do that? What kind of line do we have between A and B? Is it curved? Nope. So it's constant. So it rose 6 meters in 3 minutes at a constant rate. That's very important. Right? Next year you look at the change of rate. And once you get into that, then you start getting into a bit of calculus. Okay. Well, B to C, what happened? Did the plane, your first question, did the plane move at all? Yeah. It totally moved. Planes have to, otherwise they fall from the sky. But what happened? Yeah, it went at a constant height. Okay, so it stayed at the same height. So plane stayed at the same height. For how long? 2 minutes. Straightforward and basic. Okay, just reading what the graph is telling us. What about from C to D? What happened there? Plane did what?
The plane descended down.
Oh, good word, right? Descended. That's a good math word. So the plane descended. How far? How long? Nope. Quiet.
Tall.
Write it down. Rochelle, descended what? Yep, 2 meters in how long? Yep, 4 minutes. Perfect. Okay. And what does the line look like? Is it a curved line, flat line, horizontal line, straight line? It's straight. Okay, so what does that tell us about the rate of change? Constant. At a constant rate. Okay. That's important. Okay. D to E, what happens from D to E? Yeah, the height increases. How much? How long? So we should say the plane rises or rose, okay, or ascended is a good math word. Ascended 2 meters in how many minutes? 4 minutes. And let's describe the line. Straight or curved, and what does it mean? Straight line, so at a constant rate. So the slope is the same throughout that entire line. And the last bit, who can give me a very descriptive sentence for that? Austin? Perfect, you got everything, right? We want to mention that it landed or it's on the ground, how far, how long, constant rate. Okay, so plane descended to the ground or landed. I'm just going to put brackets here. 6 meters in 2 minutes at a constant rate. Okay. It's important to note that constant rate. I know it seems ridiculous over and over, but it is important. Any questions about explaining it? Okay, turn it over. So, have a read, please. Doing a little science graphing here. What's the unit for Josh's time? Is it minutes, seconds, G-Unit? Hours, yeah, definitely. Okay. You put hours in the brackets. Okay. What about Kayla? Kayla's time? Hours again. Okay, it says that in the sentence. So every 2 hours for Josh and 2 hours for Kayla. Temperature for Kayla, what's the units? Degrees Celsius. So a degree sign and then capital C. Oh, good. Which one's the X value and which one's the Y value?
Time is X.
Yeah, time is X. Almost all the time it's X. Okay, and that would be your independent. And then this would be your Y value, and that would be your dependent. So the number of bees depends on time. Kayla, this would be Y, this would be your dependent, so the temperature depends on time. Okay, so we're going to graph them, but before we graph, let's answer this question. Do the graphs represent functions? Looking at your data points, do the graphs represent functions?
Yeah.
How many outputs? Okay, so Jaden says yes, and I ask why. Because yes is 0 marks. Kevin?
Because the input has
No, sorry. Each input, write this down, has 1 output. Yeah, it's kind of funny, that block, isn't it? You know what's funny about... Okay.
Oh.
Good. Next one. Should you join the points?
no.
Well, look at the number of bees, right? Does it make sense to have a value in between 1 bee and 2 bees? How many bees would be in between 1 and 2? None. You can't have half a bee. So for Josh, it doesn't make sense. What about for Kayla? Does it make sense to join her points together? Yeah, temperature, what's in between 1 degree and 2 degrees? 1.1, 1.2, 1.3, all the decimals. So for Kayla, it makes sense to have values in between. Josh should always be whole numbers. Okay. All right, let's have a little look at this then. Now, whenever you start drawing graphs, you want to make sure you draw an axis. Your axes should be inside the line. Okay. So do not go to the edge of the line of the graph paper. It should be slightly on the inside. So we're going to have time on the bottom, and that will be in hours. So put your units in brackets. This will be number of bees, and number of bees are just whole numbers. So you don't have units. You measure bees and bees, just to let you know. Okay. So let's count the squares. We have 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16 squares. Okay. And how many bees does he have to count? 26 bees. So let's divide them to see how many bees per square. So what's 26 divided by 16? What'd you get? No. 2 would be 38. 1.6 something? 1.6. So what we're going to do is we're going to put 2 bees per square. Then we can maximize our graph. Make it as big as possible, but still use nice numbers per square. So we start at 0, 2, 4, 6, 8. Don't write on every line. 10, 12, 14, 16, 18, 22, 24, 26, 28. Okay, if you write on every line, it makes it look too scrunched up. Okay, so every other line or every 2 lines or something, every 4 lines. Okay. Then for time, we're going to cheat a little bit. We're going to use a little squiggly line. Okay, and we're going to start at 5 hours. So I count again. 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, 15, 16, 17. Okay, so 17 squares. And he's got how many hours? 19. But remember, we don't need 5 of them because we're starting on line 5. So really it's 19 minus 12. So what we can do is we can go, it's less than 1, like 0 point something. What is that, 0.12 divided by 17? 0.7. So what we can use is 1 square per hour. Okay. So the reason why I got 12 is because it's 19 minus 5. We're going to start at 5 hours. So this would be 7, 9, 11, 13, 15, 17, 19. Okay. Plot the points. Okay. At 5, there's 2 bees. At time 7, there's 5 bees, so I'm in between lines. At 9, there's 26 bees. At 11, there's 20. At 13, there's 21. At 15, there's 14. At 17, there's 10. And at 19, there's 1. Okay. Now, I'll be honest with you, sometimes it's helpful to plot your points first. Look at your graph, and then you can decide whether to plot the points or not, too. Okay. So connect the points. Any questions? It's always good to give it a title as well. Okay. So what's the title? Well, we don't really know what he's plotting, so let's just say it's Josh's data. Okay, always want to have a title for your graph. Because I think he's plotting probably how many bees came to a flower. or in the hive at every hour or something like that, every 2 hours. I'm not sure. So that's Josh's data. What should we title the other graph? Yeah, Kayla. We know she's measuring temperature versus time. We don't know exactly what it is. Okay. So for her graph, we can do the same thing. Count the squares and set up our axes. All the awesome things that we like to do. Okay. I'll cheat a little bit. There's the temperature in degrees Celsius. Time. The same. She's the same amount of time, so we know it's going to be the same. So we can start at 5, and we can go up by 1, because it's going to be exactly the same as she measured over the same amount of time. Okay. Otherwise, we count the squares and divide so we can maximize our graph. Now, on your graphs for your homework, don't go super crazy huge, right? Keep them about half a page, quarter of a page. Okay? Good. Temperature, we start at 0, and she goes up to 26 degrees, which is the same. So let's keep it the same. Okay, going up by 2s. Right? 2, 4, 6, 8. Who do we appreciate? 14, 18, 2. Oh, I messed up there. 10, 12, 14, 16, 18, 20, 22, 24, 28. Okay, you can plot her data. At 5, it's at 12. It's 12. At 7, it's 13. At 9, it's 15. 11, it's 19. 13, it's 24. 15 is 26. 17 is 25. And at 19 it's 21. Okay. So from this one, when you look at this graph, what does it look like? Goes up and then down. Up and then down. And so since there's measurements in between, we can connect these dots and it kind of makes a smooth curve. Okay. So that's kind of the relationship that you're going to look at. You don't have to connect them always quite rigidly. You can make a smooth curve. Okay. Questions? Comments, concerns? Okay, I'll give you a couple more seconds just to finish that off. Oh, actually I don't. We don't have that time. So, discrete data and continuous data. We have two examples of that right here. So discrete data are data values on a graph that are not connected. You're dealing with whole items. Okay. So that's exactly like, number of bees, cars, people, things like that that are whole, either discrete data. There is an exception, and that's when you're using large numbers. And I'll show you that example down below. Okay. So large numbers. Continuous data, that's when the values on the graph are connected. And that's because there's in-between measures. Okay. So when you're measuring meters, you can have 1.2 meters, 1.3, all the way up, right? So it makes sense to have data points in between. Okay. Good. A graph of discrete data can only show points because the values in between them have no meaning. So here's your little exception. If I'm talking about the number of cars sold, if I'm dealing with, 1, 2, 3, 4, I totally would not connect those points. Okay. However, if I have large numbers, so for example, this one is a graph of a dealership. Now this is a graph of Canada. So this would be the same thing, number of cars sold, but it was in the thousands. Okay. And I did 1,000, 2,000, 3,000. Well, guess what? I would totally connect those points. Why? Yeah, well, the numbers are so huge. In between 1,000 and 2,000, there's a whole bunch of values, right? 1,001, 1,002, and so on and so forth. So because the numbers are so huge, it does make sense. That's just an exception. You don't see it too often, okay? You got to come up, think about what is it you're graphing. Does it make sense to connect the dots or not? And often in the newspaper, they're the worst, right? Those are some English guys. They don't know what real numbers and math means. They connect the dots when they shouldn't. Okay, so don't think they're doing it properly. It's just some guy trying to make his living. And he probably didn't do well in math, but he did awesome in English. But he's trying to make a graph when he really shouldn't do it. Okay. Any questions? Okay. Let me just stop that. Okay. Pause.